For decades, our search for alien life meant scanning the skies for radio beacons, waiting for a signal. But then, an object called 3I Atlas appeared, and everything changed. It was racing towards our solar system, but it was slowing down. Officially, its change in brightness was just simple physics. But over 4 weeks, its light surged 5 times more than anyone expected. At the same time, spectrographs revealed traces of metal that looked like they were forged, not naturally formed. And defying everything we know about comets, it streamed visible gas but barely even changed its course. If this object is natural, we can't explain any of this. But if it isn't, we might have just witnessed our first interstellar visitor under intelligent control. So, what's really hiding behind these impossible signals? Radio telescopes have spent generations sweeping the sky, listening for a single artificial pulse, a whisper, a coded invitation from another world. But in all that silence, a different channel has opened up. Every so often, a solid object crosses the vast gulf between stars and enters our solar system. If a macroscopic technosignature exists, this is what it would look like, not a signal but an object. Since the dawn of modern astronomy, we've only confirmed 3 such visitors. The odds are just staggering. For every 100 billion comets that circle our sun, only 1 or 2 have come from another star. Each arrival is like a cosmic lottery ticket, a chance to find something that was built, not born. The traditional search for extraterrestrial intelligence, with its focus on radio and laser signals, assumes that other civilizations would broadcast their existence. But what if the best evidence is physical, silent, and just drifting through space? Objects can preserve information, technology, even intent, long after their makers are gone. Unlike a fleeting signal, a physical artifact endures. It can be studied, measured, and if the timing is right, maybe even intercepted. The sheer scarcity of these interstellar objects makes every single detection a global event. We had Oumuamua in 2017, Borisov in 2019, and now 3I Atlas. Each one is a singular opportunity, a probe from a time and place we may never see again. Their rarity means that even a single anomaly carries enormous weight. The universe doesn't offer many second chances. The original vision for finding aliens was shaped by the tools of its time: giant radio dishes, signal processing, and a search for patterns in the cosmic noise. But the discovery of Oumuamua completely rewrote the playbook. Suddenly, the search for technosignatures wasn't just about what we could hear, but what might be passing right by us. 3I Atlas isn't just another comet. It is evidence in transit, a messenger from another system. And if we're prepared to look closely enough, it might just be a sign that we are not alone. It all started on May 7, 2025. The Transiting Exoplanet Survey satellite, or TESS, recorded a faint, fast-moving object against the dense star fields near the center of our galaxy. At the time, no alerts went out. The signal was buried in a digital sea of stellar clutter, its movement too subtle for automated triggers, its glow lost among thousands of background stars. For nearly a month, the object swept onward, captured night after night in the satellite's full-frame images. Each exposure stacked another faint trace onto archival hard drives. It wasn't until July 1st that the ATLAS survey, scanning from its observatory in Chile, finally flagged an anomaly. The object had brightened sharply, 5 times more than when TESS first saw it. Yet its position was still nestled in the crowded bulge of the Milky Way, a region notorious for hiding things in plain sight. The Minor Planet Center logged the alert, and within 24 hours, observatories all over the world pivoted to follow up. In the days that followed, teams combed through old data. The Zwicky Transient Facility and Pan-STARRS both turned up pre-discovery images from late June. Their own records showed the object's trail as it moved steadily across the sky. Amateur astronomers joined the hunt, sifting through public archives and filling in gaps from mid-June all the way through the end of the month. Each new data point added detail to its light curve, revealing a surge in brightness that defied any simple explanation. The problem was the sky itself. The object approached from the direction of Sagittarius, which meant that even our most sensitive surveys struggled to separate its signal from the background. Only after the July announcement did the full scope of its early activity become clear, thanks to a massive forensic sweep through terabytes of archival data. For the TESS and ATLAS teams, the discovery wasn't a single spark of insight, but a slow burn, a fire that was lit weeks before anyone even realized an interstellar visitor had arrived. Between May 7th and June 3rd, 3I Atlas brightened by a factor of 5. This is an increase that completely defies the usual playbook for distant comets. Standard geometry predicts only a modest rise, maybe 1.5 times brighter, as the object moved from 6.36 to 5.46 astronomical units from the Sun. Instead, data from TESS, ZTF, and ATLAS all showed a 5-fold surge steady and persistent across nearly 1 billion miles of travel. Each survey's numbers line up perfectly, cross-checked against field stars and synthetic solar analogs. This isn't a brief outburst or a glitch in the instruments. The light curve, reconstructed from nightly observations, draws a clear arc rising smoothly, even as the object threaded through the crowded galactic bulge. At that distance, over 6 astronomical units away, activity isn't expected. Water ice stays frozen solid. The Sun's warmth is a distant memory. Yet, the object's coma, the fuzzy envelope around it, was already visible. Dust measurements jumped from about 300 square kilometers in May to over 1,700 by July. The numbers hold up under intense scrutiny, with error bars so tight they rule out random scatter or background confusion as the cause. When you stack up all the data, the odds tilt sharply away from geometry alone. The excess light demands an explanation, one that fits both the timing and the scale. No single survey, no matter how deep, can account for the magnitude of this change. The data, laid bare, leave little room for ambiguity. 3I Atlas was already active and already an outlier before it ever made the official record. The search for answers begins with those numbers. A 5-fold jump in brightness outpacing every geometric prediction demands more than just a passing glance at the data. Astronomers ran through the usual suspects: instrumental error, background confusion, a lucky line of sight through the galactic bulge. Each one was tested, cross-checked, and ultimately found wanting. The light curve held steady across different telescopes on different continents. Its arc was too smooth for a fluke, and it happened too early for classic cometary activity. Some suggested the object's closing speed might have been underestimated, masked by the dense star fields of Sagittarius. But even after correcting for crowding and recalibrating the data, the excess brightness remained. The numbers simply don't add up to a natural, slow-burning comet. That leaves the door open to bolder ideas. Could 3I Atlas have fired thrusters? An engineered braking maneuver to match the velocities of our solar system? It's a hypothesis that lives on the fringe, but the timing fits the data perfectly. A controlled deceleration, executed far from the Sun, would explain the early, persistent brightening without relying on water ice or familiar chemistry. If so, the object's activity wouldn't be an accident of nature. It would be the signature of intent. Yet for every speculative leap, there's a counterweight of caution. The sky is notorious for tricking even the most careful observers, and the burden of proof for extraordinary claims is heavy. As the debate turned, attention shifted to the chemistry of the coma, where the next clue might be hiding in plain sight. Spectrographs at the Very Large Telescope, tuned to the faintest whispers of atomic light, picked up a puzzle in the coma of 3I Atlas. Nickel lines, clean and well-resolved, rose above the background noise. Yet iron, which should have been there in lockstep with the nickel, was nowhere to be found. The team at the Paranal Observatory spent nights double-checking their calibrations, rerunning corrections, and cross-referencing laboratory wavelengths. The data was solid. The nickel was real, and the iron was missing. This strange chemical signature, combined with its bizarre behavior, deepens the mystery of 3I Atlas and keeps us asking, what is this object? What if I told you there is an object in our solar system that defies everything we know about comets? An interstellar visitor that's rewriting the rules of astrophysics, leaving scientists with more questions than answers. This is the story of 3I Atlas, a cosmic enigma that's challenging our understanding of the universe. The first clue that something was wrong came from its light. Using the Very Large Telescope, astronomers led by Dr. Sofia Cardenas analyzed the cloud of gas and dust surrounding the object, its coma. What they found was astonishing. The spectrum was flooded with the signature of nickel, but iron was almost completely absent. This is a huge red flag. In our solar system, iron and nickel are cosmic partners. They're forged together in the hearts of dying stars and locked in the cores of planets. Our own sun has about 18 atoms of iron for every one of nickel. Even the most metal-rich comets we've ever seen might have nickel outpace iron, but only by a little. With 3I Atlas, the ratio was completely off the charts. We're talking at least 15 times more nickel than iron, maybe even 50 times more. The team tried everything to find the missing iron. They stacked images, searched for faint signals, and probed every corner of the data. Nothing. The iron was simply not there. This elemental imbalance is a puzzle. How do you separate iron and nickel so perfectly in nature? Some theories suggest exotic chemical processes, like a fragile nickel compound vaporizing at low temperatures, leaving the iron behind. Others propose that this separation happened billions of years ago when the object first formed. But these are just theories, and none of them fully explain what we're seeing. The sheer amount of nickel, pumping out at a rate of 4.6 grams per second, with no iron in sight, is unprecedented. It's so strange that some have quietly wondered if it could be something else entirely. Could this be the residue of an ancient technology? The eroded remains of nickel-rich superalloys from some long-dead engine? The spectrum doesn't show any signs of propellants or fuel, just that lone, baffling signature of nickel. For now, the mystery remains a glaring anomaly in the cosmic ledger. But the weirdness doesn't stop there. The second major paradox of 3I Atlas is how it moves. Or rather, how it doesn't. When a comet gets close to the sun, the ice on its surface turns to gas, shooting out in powerful jets. This outgassing acts like a tiny rocket engine, pushing the comet's nucleus and altering its path. We call this a non-gravitational acceleration, and it's a standard feature of active comets. We can measure it, but 3I Atlas barely budges. Astrometric data from July through August shows it drifting by only about 1 to 1.5 kilometers per day. That's a crawl. For comparison, the last major interstellar visitor, 2I Borisov, was pushed around by about 100 kilometers per day. That's nearly 100 times more than what we're seeing with 3I Atlas. This is deeply strange because we can see the activity. Images clearly show a coma, a tail stretching for hundreds of thousands of kilometers, and even visible jets of material. All the signs of outgassing are there, but the rocket effect is mysteriously suppressed. The physics just doesn't add up. Models that take into account the comet's size and the amount of material it's shedding predict a much larger drift. The numbers simply refuse to cooperate. So what could explain this? One possibility is that the object is incredibly massive. If it were a truly enormous mountain of rock and ice, the jets wouldn't have enough force to move it. But our measurements of its brightness and size put strict limits on how big it can be. It's large, yes, but not impossibly so. It's not massive enough to be immune to its own jets. This leaves us with a mind-bending alternative. What if the object's movement is being controlled? Could it be using active stabilization, constantly correcting its course to maintain a pure gravitational path? Or perhaps it possesses some kind of advanced shell that absorbs or redirects the thrust from its own outgassing. No known natural mechanism can fully explain this disconnect between what we see and what we measure. Each new observation only deepens the mystery, tightening the error bars and confirming that this object is not behaving like a comet. It's moving through our solar system as if it's immune to its own physics. In the natural world, motion follows mass and force. But with 3I Atlas, the rules seem to bend. So we have an interstellar object with a chemical composition unlike anything seen before and a trajectory that defies the laws of cometary physics. The evidence is clear: an extreme nickel-to-iron ratio and a near-total lack of non-gravitational acceleration, despite visible outgassing. These aren't just minor quirks. They are fundamental contradictions. While Borisov was a textbook interstellar comet, 3I Atlas is a paradox wrapped in an enigma. Is it a natural object with a formation history so alien that it breaks our models? Or are we looking at something else? The silence of the iron and the stillness of its path leave us hanging, staring into the void and wondering what else is out there. The search for answers continues, and with each new piece of data, the story of 3I Atlas only gets more compelling. What do you think is going on with this mysterious visitor? Let us know your theories down in the comments. Hey everyone, and welcome back. Today, we read diving deep into one of the biggest mysteries in modern astronomy, the strange visitors from beyond our solar system. We had 3 so far, and each one has completely upended what we thought we knew about the cosmos. Let's start with 2I Borisov. When it swung through our neighborhood, astronomers clocked its non-gravitational acceleration. That's the push it gets from something other than gravity. For Borisov, this push was about 10 microastronomical units per day. That might not sound like much, but it translates to a drift of nearly 100 kilometers every single day. Every little jet of vapor escaping its surface nudged its nucleus, and every outburst showed up clearly in its orbit. In short, Borisov behaved exactly like a comet should, following the textbook physics of mass loss and solar heating. It was a reassuring, if fleeting, glimpse of a familiar object from an unfamiliar place. Then, there was Oumuamua, the first interstellar object we ever detected. And it played by no familiar rules at all. Unlike Borisov, it had no visible outgassing, no dust, no coma, nothing. It looked like a dead rock. Yet, its path veered sharply as it rounded the sun, showing a non-gravitational acceleration of 2.5 times 10 to the -4 astronomical units per day. That's a staggering 37,000 kilometers of drift every single day. All of this without a single visible jet or tail to blame it on. Its rotation, a steady 3 turns per day, only deepened the puzzle. Our models just couldn't make sense of it. It seemed to have too little mass to be a classic snowball comet, but it showed way too much movement for a simple rock. Oumuamua was a true enigma. Now a third visitor has entered the ledger, 3I Atlas, and it's thrown us yet another curveball, but in the complete opposite direction. This time the coma is undeniable. It's a huge fuzzy cloud of gas and dust. Its tail stretches for hundreds of thousands of kilometers across the sky. By all appearances, it's a very active comet. And yet, when we measure its drift, it barely registers. The non-gravitational acceleration is just 1 to 1.5 kilometers per day. That's 100 times less than Borisov, and a tiny fraction of a percent of Oumuamua's mysterious push. The rocket effect, which should be strongest in a comet this active, is almost missing. But with Oumuamua, the rocket effect was present where it should have been completely invisible. 3 objects, 3 completely different patterns, and none of them fit the same mold. The universe, it seems, loves to keep us guessing. So how do we solve this? How do we prepare for the next visitor? Enter the Vera C. Rubin Observatory, perched on Cerro Pachón in Chile. Its massive 8.4-meter mirror is poised to sweep the entire southern sky every few nights. This isn't just another telescope, it's a game-changer. The project, called the Legacy Survey of Space and Time, or LSST, is heralding a new era of early warnings. Its incredible cadence and sensitivity mean that the next interstellar visitor, whether it's a comet, an asteroid, or something far stranger, won't slip by unnoticed in a crowded field of stars. When it detects something, alerts will go out in real time. This gives both professional astronomers and amateur skywatchers a running start, a chance to point Gigic telescopes at the object after it's discovered. But big telescopes alone can't catch every twist and turn. The last 2 interstellar objects prove that. When 3I Atlas suddenly brightened 5-fold against the dense star fields of the galactic bulge, it wasn't a professional survey that first pieced it all together. It was amateur astronomers. They tirelessly trolled through terabytes of archival data, stitching together the first clear light curve, tracking its brightness over time. A global network of citizen scientists, armed with their backyard setups and open-source software, filled in the crucial gaps between the big survey passes. Their rapid reporting turned a handful of scattered images into a coherent timeline, catching activity that would have otherwise vanished into the noise of the data. This collaboration is the new frontier of astronomy. And now, the stakes are higher than ever. As 3I Atlas continues its journey around the sun, every single night counts. Coordinated campaigns are underway, creating a global net to catch every detail. We have the Rubin Observatory's nightly sweeps, the Pan-STARRS telescope in Hawaii, the Atlas survey in Chile, and a constellation of amateur stations from Pretoria to Perth. Each observer, no matter how small their telescope, adds a crucial data point. They help shrink the error bars in our measurements and sharpen the models we use to understand these objects. The next outburst, the next spectral anomaly could come at any hour, from any direction. And when it does, the early warnings will ripple through Discord servers and Telegram groups, triggering impromptu follow-up observations from telescopes large and small, all over the world. The call to action is simple: eyes on the sky. Track the light curve. chase the spectrum, and share everything the raw frames and the calibrated data. In this new era of solar system exploration, discovery isn't just reserved for a handful of professionals with access to the world's biggest observatories. Every alert, every image, every single measurement is a step closer to catching the improbable, to understanding these cosmic messengers. We might be looking for a message written not in radio signals but in motion, chemistry, and light. A puzzle broadcast across the stars, waiting for us to piece it together. And the pieces we're finding are bizarre. Recent spectroscopic observations of 3I Atlas from the Very Large Telescope in Chile have shown nickel in its coma, but strangely, no iron. This is a highly unusual chemical signature for a comet. At the same time, astrometric fits, the precise measurements of its position and trajectory, reveal almost no non-gravitational acceleration, even as we can clearly see it outgassing. This directly contrasts with 2I Borisov, which displayed typical cometary drift, and 1I Oumuamua, which showed a significant change in its trajectory without any detectable outgassing at all. These opposing anomalies remain completely unexplained by our current models. Now, to be clear, there's absolutely no evidence to confirm any kind of artificial control or technology. But the profound physical contradictions in the behavior of objects, like Oumuamua and 3I Atlas, are a direct challenge to our accepted theories of comets and asteroids. It forces us to ask new questions and consider possibilities we might have previously dismissed. It seems our best clues about what's really out there in the vast interstellar dark may not arrive as clear signals, but as quiet, puzzling objects whose very motion defies our expectations. The universe is speaking to us, and we're just beginning to learn its language. Thanks for watching. If you enjoyed this journey into the unknown, be sure to like, subscribe, and hit that notification bell so you don't miss our next deep dive. See you next time.